the feasible set of the above optimization problem is given by this. Given that, what choose the correct statement? This is a pretty easy question. I can like, let me share my screen and I can tell you. Do you have any specific query?
No, apart from this, I don't have any other query.
Okay. No. In this question, do you have any specific query?
Sir, my doubt is if nothing is mentioned, so how we can just say whether the domain and the feasibility will be convex set or not? Because the constraint or even the objective function can be non-linear or non-convex.
Yeah. So that was the inherent assumption. Sorry, like, apologies. We did not made it very clear. But this basically the function f0 of x, which is given to you, is a convex function, right? So a convex function, can you tell me one thing? So if I had a f0 of x, okay, this is the function and it is convex. Okay, so what can you say about its domain? Domain of x. What can you say about its domain?
Convex set.
Why?
Because this function is convex, so obviously its domain should be convex set.
Okay, but I get your point and you are correct, but this is not a valid argument that it is convex, so it should have a convex. Can you like think of a better argument or a better reason why this should be a convex set? A domain should be a convex set.
Okay.
Okay, so what is the property of convex functions? F of, I guess you are comfortable with the notations, right? This,
yeah.
Understand what I mean by this. F of theta x into 1 minus theta x. You know that theta and 1 minus theta, they belong to 0 and with 0 to 1, right? Okay. So what is this? This is the convex combination, right? And you know this property of convex functions, right? So this basically this if the set is not convex, will this point be defined?
No, it won't be defined.
It won't be defined, right? So that is why if a function is convex, it implies that the domain is also a convex function. So this is a very intuitive. It is not the rigorous proof, but it is a very intuitive one. Okay.
Okay. So in question by default, we have to assume that the problem is convex.
Yeah. So definitely, whenever you see such a problem of constraint minimization, I forgot to mention it explicitly because I thought I was also a bit biased because I was studying this convex optimization. So yeah, it was my mistake, but apologies for it. But definitely, like, it was quite clear that the function is a convex. This optimization problem is a constraint optimization, is a convex optimization problem. Okay, so this is it, and we got to know that domain of the objective function is a convex set. Okay, so this is clear, right? The first part is clear.
Yes, sir.
Domain of f0. I'll also write it in this one, in the same notation as in the question. So domain of f0 is a convex set. Okay, it's convex. This we have seen, right?
So if domain is convex, then obviously feasibility set will be convex.
So let us get it like one by one. Okay. Domain of the problem D is not this. It is the intersection. So let us take it one by one. Now tell me, what are these FIs? Fi of x. What are these? These are the inequality constraints, right? These are the inequality constraints. And for a convex optimization problems, what is the condition? First of all, what is the condition for a optimization problem to be a convex optimization problem? I'm not asking very rigorous. Just tell me a rough idea, like what do we mean by when we say that a problem is a convex optimization problem?
Objective function should be convex, and this domain should be convex set.
That is clear. What about the inequality constraints?
All the inequality constraints should also be convex function, and equality should be affine set.
Okay. So let us. Okay. So this is what I just wanted to hear. Okay. So these are also what? These are also convex functions, right?
Yeah.
Convex functions. So domain of Fi of x will also be a convex set then, following the same argument, because if it is not convex, then the convex combination won't be defined. So domain of Fi of x, it will also be a convex set. Okay, so we are done with this part. So convex set. Now tell me about the equality constraint. So Hj of x equal to 0. Okay, so when we have such an equality constraint, and it was given that the domain of hg of x is entire Rn, right? It was
Yes.
given that domain. So this yani ki domain of hj is a convex set. The entire Rn is a convex set, right?
Yeah,
You agree with it? Domain
I
of
agree.
hg of x is a convex set. Okay. So now what is the domain of the problem? Domain of the problem is the intersection.
Yeah.
This is the domain, right? This this is the domain of the problem. Is this visible?
Yes, visible.
So you know that this is a convex because it is a convex function, right?
Yes, sir.
It is also a fi's are also convex. So basically, this also becomes a convex set because fi is a convex function. So domain of fi will be a convex set. Am I
Yes, sir.
clear?
Yeah.
And domain of hj is entire Rn only. So it doesn't even matter if I take an intersection with this or not. If I take an intersection, will it matter? Like intersection with Rn, any intersection I do, will it matter? Rn is the entire set. So anyhow, this is like if I take the intersection with Rn, like only these things will matter. So therefore, and you know that intersection of two convex set is a convex set, right?
Yeah.
You know this part, right? Intersection of two convex sets is a convex set. So therefore, D becomes convex. Am I clear?
Yes, sir.
Okay. So now basically what happens is that I'll also like try to make do you, like that is the difference between D and F clear to you? Like D, which is the domain of the problem, and F, which is the feasible set of the problem.
Yes, sir. The difference is clear to me.
Okay, could you just tell me like so that other people could also like just say what is the difference between D and F? Like which one of them has a greater number of or a greater cardinality?
Uh,
Which
D, D is
D,
domain. Domain means the set of values which X can take, and
right? But
feasibility
it
means
yeah, but
X which
so
will satisfy the constraints also.
constraint, yeah, exactly. So in domain, there can be values which do not satisfy the equality constraint, or which do not satisfy these constraints. Okay, there can be values which do not satisfy these. In domain, we can have because fi of x can have the domain of entire Rn, right? But whether the condition is satisfied or not. So suppose we say we have a function this. So this has a domain of entire Rn, but fi of x less than equal to 0 is satisfied only in this part. So this would be in the feasible set. Am I clear on this? Or any
Yes,
confusion?
sir. It's clear.
So this is the function. Okay. So now one question for all of you in the meeting. So we just like I'll paste it again. So I hope Tanuj, your question is clear. Do you have anything related to this, or shall I proceed?
No, no. My doubt is clear now.
Okay. Okay. So sorry, it is. Okay, so this is the problem. Assume that f naught is convex. This is the convex optimization problem. This is also convex. What if I say that hj of x is also convex? So will it be? What can you say about the domain then? If I say that hj of x equal to 0, first of all, tell me whether it can be a convex. It can be a convex or not. A convex set. The domain of hj of if I take hj of x equal to 0, not domain. Let us leave the domain. Just tell me what will be the feasible set.
Sir, can you repeat what the change you are making now?
So okay. So I'll start from the beginning. We have f naught of x, which is a convex function, right?
Right.
We have fi of x, which is a convex function. We have hj of x equal to 0, right? And I'm saying that hj of x is also a convex function this time. Okay. So leave d, but tell me what will happen. What will this set f be? Will it be a convex set? You can look like it is x belonging to d, where this constraint is also satisfied and this constraint is also satisfied. So what do you guys think that if hj of x equal to 0 is a convex function, hj of x is a convex function, or hj of x, this hj of x is a convex function. So this hg of x is a convex function. So what can we say?
I think that still the feasibility set will be convex.
Okay. Anybody else? What is anybody like in the call? Like, what is his or her opinion? Will this if hg of x is not affine, it is a convex function. So what will be like? What is your opinion? Whether this feasible set F be a convex set or not? Anyone? We have like 7 to 8 people sitting in this meeting.
Yeah, maybe not, because when we
Sorry.
have hx equals to 0,
Hmm.
the convex state, it will be bounded. Something in affine will have the whole plane, but convex state are always bounded. And if
Yeah,
x is
you're on the correct line. Okay, so let me make it. Okay, so let us consider this function. Let us consider this function. Okay, so let us consider this function. So is this convex? First of all, tell me, is this a convex function? A yes or a no?
Yes, sir.
It is a convex function. So like what hj? Let us say this is the hj of x. Now, what is the solution to hg of x equal to 0? What is the solution of to hg of x equal to 0? These 2 points, right?
Yeah.
Only these 2 points. So when I take the intersection, what will my f be now? If I take intersection, let us consider that this part is satisfied, every point satisfied, this is entire Rn. So what will be my f? What will be my f?
These 2 points.
These 2 points P1 and P2, right?
Yeah.
So if I have only 2 points P1 and P2, so is this set a convex set?
No.
No, right? Because what about every point that lies on this line segment should be basically contained in this set, right?
Yes,
What
sir.
do we mean by convexity? If I have P1 and P2, then every convex combination of P1 and P2, that is theta times P1 plus 1 minus theta times P2. This should lie in the set, right? But we only get 2 points over here. Or if we consider this, so we only have 1 point. So that is why what we take hj, that is why we take hj to be an affine function, so that the hg of x equal to 0, we get an entire plane. Okay, so what you know that hj of x equal to 0, this would be representing an entire hyperplane in Rn, and you know that hyperplane is a convex set, right? Any confusion? Tell me, with hyperplane a convex set or not?
Yes, sir. Convex set.
It is a convex set, right? So that is why we do, like when I was studying convex optimization, my first intuition was that why is not this function convex? When this is convex, why is this function not convex? But then like eventually my professor told me that if this hg of x becomes convex, hg of x equal to 0 will have finite solution. Okay, finite points. And whenever you have finite points, you cannot have every convex combination of it in that set. So this feasible set will be no more. It will not remain convex anymore. So this is like where we like this is what basically troubles us. So that is why we take hg of x equal to 0, and hg of x is an affine function. Okay, so one more question. Okay, one more question for all of you. So what is the difference between an affine set and a convex set? You know that affine combination and convex combination looks very similar, very similar. What is the difference between them? Anybody? Affine sets and a convex set? This is a pretty basic question.
so basically, if in a domain, it will take on 2 points. So the
Sorry, you're not clearly. Could you just adjust your mic if
process,
possible?
is it clear now?
Haha.
So like if any domain we take any 2 points,
Hmm.
so if uh, the domain, like if there is just the line segment lies
Hmm.
within that domain, then that is convex set. But if
Hmm.
the line passing through those 2 points also line in the domain, so that is affine set. For example, like any say
Okay.
R2 plane is affine set, but if we
Hmm.
take a circle in that R2 plane, that is a
Hmm.
convex set.
Okay, so yeah, it's pretty. It's you are pretty correct. So basically, in affine set, what we talk is a line. If we take 2 points, okay, if we take 2 points, then we basically check for an entire line segment, entire line. Not sorry, not line segment. But in this, we check for a line segment. Okay, so just tell me one thing. If I take, I guess it would be more clear. If I take this is a disk. Okay, and it is completely shaded. So it is like it is completely filled. Okay, it is completely like it is a disk, not a circle. It is a disk. All the points in it are in the set. Okay, consider this set a disk. Okay, is it clear? Like what is the set? All points in the including the boundary, also including the boundary, all points inside this. Okay, so is this an affine set?
No, no, this is not a.
But is this a convex set?
Yeah, it is the convex.
So why? So let us consider these 2 points, two boundary points. Let us say. Let us consider two boundary points. So let us consider this is the first boundary point and this is the second boundary point. So if I draw the line between them, what will the line look like? The line will look like this, right? So is the line contained inside the set?
Yeah, no,
No, right? But what if I draw a line segment? How will the line segment look like?
inside this.
This will this is what line segment will look like, right?
Mm,
And the line segment is contained inside this set.
yeah,
So this is the convex set, right?
yeah.
Okay, so Tanuj is asking what is the difference between linear function and affine function? So basically, it's a good question. Affine function and linear functions look similar, but you know that linear functions are also functions like f of ax plus by. It is a times fx plus b times fy. Do you know this property of linear functions?
Yes, sir.
So yeah, so linear, like I'm not like very sure about this like what is different between linear and affine, but this is what I know that linear functions have some more strict rules to follow, whereas affine functions don't have. So all the linear functions are affine also are affine. So it is just like any that have these functions ax plus b. These are affine as well as linear. So this is what I know. I'll also check if any major difference I could spot, and then I'll get back to you on the discussion forum. Okay.
So
Okay, sir.
like I have one like point. Is it
Uh,
correct or wrong? So like basically in linear algebra or anything, so linear functions basically means the rotation of the domain, right? And affine and the origin is fixed. So whenever we do any affine linear transformation, the
hmm.
origin is fixed. But when we do affine transformation, the origin gets shifted. So that's the difference. Like,
I'm really not sure about it, but I'm getting what you're saying that whenever we do a linear transformation, we do not shift the origin. But when
yeah,
we do an affine transformation, the origin will be shifted. I guess when we put 0, 0 over here, the origin basically will be shifted. The
yeah,
origin,
that
like
is
the
plus
plane
b
will not
constant.
pass through the origin. I get it, but this is also a linear function. So I'll check and get back to you on this.
Mm.
Okay, so another thing that we have is okay, affine sets and pretty clear thing. So can we see that every affine set is a convex set or not? Can we say this? Every affine set is a convex set.
No, sir, but
I guess
vice
this was
versa
pretty
is true.
basic. Everybody could
Yes,
answer
yes. So
it.
we can say it, yeah.
No, we cannot say.
Am I audible?
Yes, sir, you are audible.
Am I audible? I just lost the connection somehow.
Yes, sir, now you are audible.
Okay, so this is the question. I was just waiting. Why is no one answering this? So is every affine set a convex set?
No, but vice versa is true.
Sorry, is every affine set a convex set? Every affine set is a convex set.
Yes,
Is
yes,
this
this
true?
is, yeah.
Yeah, it is true, right? But the vice versa
Yeah.
is not true because
Mm.
affine set means it contains a line in it. Remember it this way. Affine sets are those sets which contains the entire line passing through those points in them. Okay.
So,
But
sir,
convex set,
every convex set will be affine set.
no. We just looked at this example, right? This is a convex set. Disk is a convex set.
Okay,
Yes
okay,
or no?
okay. Oh, yes, sir, I misunderstood between this affine and convex. Okay,
Yeah.
yeah.
But it is not convex. Okay. So another thing that I would like to cover up on this.
Sir, I have one more query.
Please ask.
I have one query regarding that dual function.
Yeah, go ahead.
Sir told in his lecture that every dual function will be a concave one.
Right.
So how we can say actually when we find the dual function, it will be an affine function of lambda and mu. And every affine function is both concave as well as convex.
Both, yes.
So why we are saying that dual problem is only concave? It can be convex also.
Because you know that we're trying to maximize it, okay? Right. If you look at a convex function, what is the maximized value of this, or what is the maximum value of this? This is a convex function, right?
Yeah.
What is the maximum value of this function? It goes up to infinity, right?
Infinity.
But it has only one minimum value. Basically, it has only one global minimum. What does a concave function look like? This is what a concave functions look like.
Okay.
Right. So it has only one global maximum. Ideally, this is the ideal case. Like it is not the, but it is the ideal case. So this is how I'm trying to answer you. So that is why whenever we have a maximization problem, we try to quote it as a concave problem. Okay, because we know that otherwise, if it is a convex problem, we know that the function might be like going up to infinity. If it is an unconstrained function, it would be going to infinity. But this is what concave gives us the beauty that, okay, it is that we know that it will have only one global maximum. Okay. Moreover, like it is the dual function, it is concave for the given values. Okay. It is concave for the given values of lambda and mu. Give me a second, I'll just cross check with the lecture notes. So this is what the definition is. Okay. The dual function g at any point, the dual function g at any given values of dual variable lambda and mu. So you need to give these values of lambda and mu. Okay, so you need to give these values of lambda and mu. Okay, the optimal value of unconstrained Lagrangian, this is the dual function, right? This is the dual function, and it is a concave function given lambda and mu. So just remember that it is a concave function when we fix lambda and mu. So it is given lambda
How
and mu.
we can say, sir, this will be a concave function?
Okay, so you're asking how we can say that it is a concave function.
It is always a concave function. How we can say this?
Okay, so I'll also just copy paste the Lagrangian function over here. Okay, and then we can like discuss how we come about it. Let me check your developer. So this is the Lagrangian function, right? Given in convex optimization problem, this is the Lagrangian function. Okay.
Yes, sir.
And we know that the Lagrangian function is an affine function for any given value. So if I give you the value of x, so let us fix x. Let us fix x equal to x naught. For any given value of x, this L of x naught, lambda, mu, it will be basically like f naught of x. It would be a constant one, c1 plus a summation of, so all of these will take a value. So it will be a function of lambda. Lambda is a vector. Okay, it is a vector of n cross 1, and so it is a affine function, right? A linear sort of a function of lambda and mu. Okay, so we know that the Lagrangian is an affine function of the dual variables. Is it clear?
Okay,
Given
so it
an
is
x, yeah. So given an
value
x,
of x.
for a given value of x, the dual function is an affine function. Okay.
Okay.
So now tell me, if what are we doing in this g of lambda comma mu? What are we doing? So for if I say, okay, take one, you take one value of x, you take and you keep putting values of x, and you try to see, and you're taking a pointwise infimum, right? So pointwise, do you remember that what is the pointwise maximum of a convex function, of a family of convex functions? So we have, suppose, n convex functions, and I take pointwise maximum of it. So what is that function? Like the pointwise maximum, what is that property? Do you recall?
Yeah, it will be a convex function.
It will be a convex function, right? So here also, like we are taking pointwise infimum. So this is the Lagrangian. You keep you like try to substitute x every time. You try to substitute x1, x2, x2, and so basically you are taking a pointwise infimum in x, right? So you are taking
but
pointwise.
variable is x. We are taking infimum with respect to x.
So that is what I'm saying, na. We every time if you fix a x, what we do? What do we do in Lagrangian? If we fix a x, we know that it is an affine function. So now I'm saying you take all the possible x's. Suppose you have 100 possible x's, and you keep and you put values one by one. So what are you doing eventually? You're taking a pointwise infimum, right? If you put 1x, if I substitute the, what will be, let us say L1 will be when I substitute x1. This will be a function of lambda or mu, right?
Yeah.
L2, if I put x2, this will also be a function. L2 is when I put x2. It's not equal to, but it is. So this will also be an affine function of lambda and mu.
Yeah.
Suppose I put xn. What will I get? Ln, right?
Yeah.
And it is also an affine function of lambda and mu, right?
Okay.
It
So
is an
now
affine function, na? So now what we have to do, we have to just take infimum of them, like right? So pointwise infimum of affine is a concave function. You're taking infimum just as pointwise max, because affine functions are both concave and convex, right? So when we take
okay,
so this is how the proof goes of it. So it was.
Okay.
It is not a very mathematical proof. Sorry, I was not able to give you a very mathematical, but this is what the intuition lies behind it. So we take a pointwise infimum, and if we whenever we are taking pointwise infimum in X of family of Lagrangian functions which are affine, therefore the G is a concave function. Okay.
Okay. Okay, sir. I understood. Now I understood.
Okay. There's some questions in chat boxes. It is saying, sir, please check question 5 of assignment 7. Okay, let me check.
Sir, once I have one question here on this.
Just a second, let me check this question 5. This is a pretty serious if it needs to be reevaluated. Neeraj, if it is like, are you comfortable in unmuting yourself?
Yes, sir. Yes, sir.
Yeah. So how is the option C correct? We just discussed
So
it.
that is the definition of the convex set.
It is not a line, it is a line segment. That is the main, like, weren't we
Okay.
discussing this?
Yes,
Weren't we
sir.
discussing this in this example?
Yes, sir.
So that is why I just got scared that I'll have to reevaluate. But yeah, so this is the main difference between affine sets. When I was asking what is the main difference between affine sets and convex sets, this is what it is. The line is contained in the affine set. The convex sets are limited to the line segments, not the entire line. The line stretches from minus infinity to infinity.
Yes,
Suppose
sir.
but the line segment, so that is why if a set is convex, if we draw a line segment passing through the points, it is not a line. Okay. I hope I was able to clarify this.
Okay, sir.
Yeah, somebody else also had a question.
Yeah, so here I had a question like you mentioned, like we take a point-wise infimum for this G
Right.
lambda mu, right?
Right.
Yeah, so I think in the lecture sir mentioned like while we calculate G lambda mu, so we keep lambda and mu as constant and we minimize the Lagrangian. And from that we get the G lambda mu. So
it was
I'm
just to
confused,
give
like,
you an idea. Just to give you an idea. This is not the algorithm that will solve this problem. Okay. So
okay,
definitely, like you will take some lambda and mu, and then you go on X and you try to see. But again, you'll have to also like then find out the optimal lambda and mu. It is not that you fix it. You first need, initially you need to fix them, but then, so basically what will be L1 look like? So L1 will have, let us say, a lambda on this axis and mu on this axis. So basically you will be fixing lambda and mu. So suppose this point fix lambda and mu. This is a point. It will have a fixed value of lambda and mu, and correspondingly we'll have a value of L1 on the third dimension. Okay, so
yeah,
you'll have, so you eventually are fixing lambda and mu, but this is like considering the all possibilities. We do not consider all possibilities. We choose lambda and mu very smartly. So there are algorithms that like update lambda and mu. We also like you choose the very first one very intelligently. We do not like blindly choose lambda and mu. Okay, so yeah, so like also like I would like to talk about KKT conditions. Like, are you so is it, does anybody like having any questions in it in the KKT condition? So notes are not updated. Okay, Tanuj, I'll convey this to the team. They'll update. I guess we updated the notes. Don't exactly know.
Sir, in morning I have checked for week 7 and 8. It's not there.
Okay. Okay, I'll make sure that they're uploaded. I'm just forwarding this to the team. Okay, so can you just can somebody tell me what is the strong duality, weak duality, all these things? That this is what is important to us. Strong duality. What happens in strong duality? Can anybody just give me a gist of it? Like what happens in a strong, like when in the case of strong duality?
Lambda is strictly greater than 0.
That is always the case. In the weak duality also, lambda is greater than equal to 0.
In strong is strictly greater than 0.
In strong, it is strictly greater than 0.
Maybe.
No, this is okay. If it is strictly
The
greater than 0, okay. Just to reiterate it, do you know what is complementary slackness?
No, sir.
Anybody here? What is complementary slackness?
product of lambda and the inequality constraint will be 0 for all
For
constraints.
all I,
Inequality.
right? So first of all, so like for all these, I know that these are pretty, like, I'm not very clear with this for what I mean, but for all I, but I know, I'm believing that you guys have watched the lecture then, and you know that these are like I goes from 1 to n, all these sort of things, right? You know that what these f subscript I lambda I means,
Yes, sir.
right? Because in the lecture, and you know that we have m inequality constraint. This I goes from 1 to n or m, whatever like be the convention. Okay, so if the lambda is always greater than 0, what does it imply? If lambda is always greater than 0, what does it imply?
Fi is active constraint. It is equals to 0.
It is equal to 0. So therefore, and you know that every constraint is not an active constraint. Like it can be, but it is not. Is it a mandatory case that every constraint will be an active constraint? It is something mandatory?
No.
No, right? So strong duality does not guarantee that lambda is always greater than 0. If lambda is always greater than 0, we cannot ever achieve this complementary slackness, because every constraint will be equal to 0. And just to tell you, for a strong duality, we need to find some point that this inequality constraint is strictly less than 0. It cannot be equal to 0. If all, so yeah, I guess that is a pretty far-fetched. So just remember that in a strong duality, to prove strong duality, sometimes we need to show a point in the interior of the set for which all the inequality constraints are less than 0. So this has not been like, this is beyond the scope. So, but just to tell you, so the strong duality does not imply that lambda is greater than 0. In the initial state only, whenever we were defining the problem, then only we defined that lambda has to be greater than equal to 0. And this was defined at the time when we were trying to form our Lagrangian itself. When we were trying to form this, okay, we wanted to basically what we wanted to penalize whenever the fi of x goes is violated. What do we mean? What do I mean by it is violated? It is greater than 0, right? If fi of x is violated, it will be greater than 0, right? Right or wrong?
Right, sir.
Yeah.
And if lambda is also greater than 0, so this term would be positive, right? Positive, and so it would add up to my function value. So it would prevent x from being the minimum. If x lies outside the feasible set, it won't this function will add up something, and it won't allow x to be the candidate. Okay, and it won't allow x to be the candidate. This is the entire gist of it. Okay, this is not the mathematical proof, but this is how I remember, and it is something intuitive. You're trying to get it, and whenever like if I of x is satisfied, this lambda greater than equal to 0, it is less than 0, so the end product would be negative when it is satisfied, right? When the constraints are satisfied, it would be the product of lambda fi, it would be negative or positive?
Negative.
Negative. So it will increase the probability of x being minimum, right? Because we are decreasing something. So it would reward x. It would reward x for satisfying all the constraints. What do I mean by reward x? It would like increase the probability of x being the minimum. Okay. So this is just the intuition. So this is where we define lambda greater than equal to 0 comes in the picture. It has nothing to do with strong duality or weak duality. Okay. Am I clear on this? Is the intuition clear? Like, why do we choose lambda greater than 0?
Yes, sir,
Yes.
it's clear.
Okay. Should I? Question was Neeraj. Should I explain again?
No, sir. Thank you, sir.
Okay. Okay. So what happens in strong duality is this is what happens in strong duality. So do you know, guys, what is P star? What is P star?
Optimal value of primal problem.
Optimal value of primal problem. What is G star?
Optimal value of dual problem.
Okay. If we do not have strong duality, what is the relation between these two?
P star will be greater than D star.
Okay, yeah, so that means D star would be less than equal to P star, right? Right?
Yes, sir.
And we know that this D star, it would be greater than G of lambda mu because this is the maximum value, right? This is the maximum value. So G of lambda comma mu will always be less than D star because D star is the maximum value of G of lambda mu, right?
Yes, sir.
Right. So is this equality constraint like clear to you? Is it like, is it making sense?
Yes. Yes.
Okay. So and now we know that P star is so P star would be always less than,
F naught of Fx.
yeah, exactly, F naught of X. So now tell me what happens in the case of strong duality.
D star becomes equals to P star.
D star becomes equal to P star. So that means the duality gap becomes 0, right?
Yes.
So this means that so P star is F naught of X star, right? You know that P star is equal to F naught of X star, right? Because we will
Yeah.
have we need to have some point na X star that will give us P star, and D star is also have D star. It also has certain. It is also respect to with some lambda and mu value of some lambda and mu, lambda star and mu star, right?
Yes.
So we are okay. So we need to have some lambda star or a mu star that gives us D star, right? So
Yes.
what is okay? So what is the G of if I try to what is this function? If I try to write G of lambda star mu star, what will this function be? So this would be F naught of, what is the Lagrangian function? F naught of X plus summation of I, or for all the inequality constraints lambda I star. I'm writing this function, okay? Lambda I star Fi of X.
X comma lambda star mu star.
Sorry.
Lagrangian function is equals to हम Lagrangian function जो है वो x lambda star mu star पर होगा ना ये.
हाँ, एग्जैक्टली तो यही मैं सुनना चाह रहा था. अभी देखते हैं. तो G क्या होता है? G क्या होता है? तो अभी यहाँ पे प्लस J इक्वल टू 1 to mu star into mu J star of H J of X. तो ये तो Lagrangian हुआ और राइट, ये तो X पे भी डिपेंड कर रहा है. तो हम G कैसे निकालते थे Lagrangian से, किसी को पता है? हाउ डू यू,
हाँ, तो इसमें
हम लोग क्या करते
वो
थे? इन्फीमम ले देते हैं ना.
इन्फीमम ले.
Infimum for all X belonging to the domain of the problem. Okay. अब तो ये X का फंक्शन नहीं बचा ना, राइट?
नहीं, पर्टिकुलर X के लिए जो
मतलब हम पूरे X पे घूमेंगे और कोई एक X ले लेंगे, ठीक है?
मिनिमम होगा.
हाँ, ये D स्टार है, ठीक है? अब ये है हमारा D स्टार. तो अब ये जो इन्फीमम होगा, तो ये क्या है हमारा? ये D स्टार है, ये इसके बराबर है, ये इसके बराबर है, ये इसके बराबर है, ठीक है? अब मैं कहता हूं कि मैं एक और इक्वेशन लिख रहा हूं, उसको ध्यान से देखना, ठीक है? मैं ये इक्वेशन यहाँ पे लिख रहा हूं. f नॉट basically मैं ये equation यहाँ लिख देता हूँ, but okay, so this is the equation f naught of x star plus summation, मतलब I'm not writing all those i's, okay, lambda I f I of x star plus summation mu j star h j of x j of x star. Okay, is this equation visible to you? This equation, right?
Visible.
Right. Okay, so since we are about to end, so if anybody has any questions, so first ask it, because this is what I'm currently going through, is not a part of basically scope, but not a part of today's session. Basically, so if you have any question, first of all ask, then only like I'll take this forward, because this is something extra that I'm discussing. Anybody having any question?
Sir, in this equation, like this x star, we can say that this x star minimizes Lagrangian.
That'll come, like not related to this question, related to any assignment, previous assignment, or so if any question you have.
Okay, assignment question.
Anything? Okay, cool. So, okay, let us get back to this problem. Okay, so officially the session is over. So if anybody wants to drop, this is this extra what I'm discussing, but it is pretty useful to in building up the intuition. So tell me what can we say? What can we say about these two? This is the first equation and this is second equation. What is the relation between these two? What is the relation between these two?
सेकंड वन इज ओनली मतलब आपने एक फिक्स कर दिया कि ये एक्सिस पर ही फंक्शन जो है वो काम करेगा,
फिक्स कर दिया, तो ये पूरी इक्वेशन की वैल्यू कुछ बड़ी होगी या कुछ छोटी होगी या कुछ इक्वल होगी या कुछ लेस देन इक्वल होगी या कुछ ग्रेटर देन इक्वल होगी, तो ये 1 और 2 के बीच में क्या रिलेशन होगा, कोई मुझे बता सकता है? मतलब 1 लेस देन 2 या 2 लेस देन 1 या 1 लेस देन इक्वल टू 2, क्या होगा?
I think, sir, 1 should always be greater than equals to 2.
Greater than or less than? अरे it is infimum, so 1 will always be less than equal
less
to 2,
than,
right? Infimum, we are going on every x and we are choosing the minimum and we are trying to find the infimum of x. Here I'm just giving you any random x. It may or may not be the infimum, right?
Okay, this x star is not the optimal x.
ये फिक्स कर
We
दो,
will come to that point, but currently so it is not. It is, assume it is a general point. I will show that this is it comes out to be the optimal, but currently so it is not. मतलब currently don't go with that by. So let us say it is a general point. Okay, so this will be right, 1 greater than, like 1 will always be less than equal to 2, right?
Yes, sir.
Okay, so now I'm writing a third equation. Okay, so let me just copy it directly from here only. Okay, so not copy it, just tell me one thing. Okay, so now, okay, so now this x star lies in the feasible set. Okay, let us assume that this x star lies in the feasible set. So this term would be equal to 0, right? When x star lies in the feasible set, this term will vanish to 0.
Yeah, it will satisfy the constraint.
Exactly, right? And this would be, when x star lies in this would be positive or negative?
Negative.
Negative. So this basically, so what does it mean? This means that how should I put up that this equation, this the result, like the two equation. Second, I'm also writing a third equation, which is simply f naught of x star. So what is the relation between f naught of x star, this third equation, and the second equation? 2 less than equal to 3, right? Now tell me, is this clear or not? All these three equations are there on the board, and the relation between them.
Yes, because that is less than 0. So
Take, take 2 minutes and stare on this, like what I'm writing, and like from where did we started, and we are talking about strong duality, right? And this is not basic. This is something extra. So if anybody wants to drop off the call, feel free. If you don't have any goal, okay.
the
So
third one be F naught X star, or because the second F naught X star, it will be different.
so this is the so that's what I'm let's what commit, right? So you agree with it that this is the correct order, right? You agree, right? This is the correct order. I told you.
Yeah.
So 1 less than 2 because 1 is the infimum, 2 less than 3 because of X lying in the constraint set. So 2 would be something negative. Matlab we'll subtract, we'll remove something, right? From 2 and then we'll get to 3. Okay. So this is from where what we started. And what happens in strong duality? P star is equal to D star, right?
Right.
So what is eventually we are saying? So we are saying that F naught of X star, we start with which is equal to P star. Okay. Which is equal to D star in strong duality, right? Which is equal to D star, which is equal to G of lambda star mu star. We wrote this above, right?
Yeah.
Yes, sir.
We wrote it, na?
Yeah.
What is G of lambda star mu star? G of lambda star mu star, which is equal to infimum of, which is this
1.
This equation 1, infimum, like I'm writing 1.
Yeah.
Which is less than equal to 2. 1 is less than equal to 2.
Yeah.
2 is less than equal to
3.
So what eventually we said, like what are we saying, that F naught of X star is less than equal to X star. So is this possible? So like eventually it is, so eventually like what we'll say, we are saying that F naught of X, like we are trying to prove that like if now what we end up with, so this means that it is not less than equal to, it is just equal to. So this, what does this mean? This is how I'm just trying to bring in how does complementary slackness comes in. Okay. So this means that, okay, we said that, okay, on the 3 itself, we are saying that this is equal, right? From the point where we started and where we are ending, it means they are equal, right? Right or wrong?
Yes, sir.
So which also means that this part 2 should also be equal to 3 in case of strong duality, right? 2 should also be equal to 3. 2 should also be equal to 3. Just try to see, because what did we eventually do? We did nothing wrong. We said 1 is less than equal to 2, 2 is less than equal to 3. And then we are saying 1 is equal to 3. So it is like if 1 is equal to 3, what is the what now can we say that, okay, consider it this way, 2 lies somewhere between 1 and 3, right? 2 lies somewhere between 1 and 3, right or wrong?
Yeah, right.
If I merge 1 and 3 and make it a single point, let me turn on my camera. Just a second, let it get started. I'm having, okay. So if I merge 1 and 3 together, it's like it will become a single point, right?
Yeah.
Are you getting it or not? This is 1, this is 3. 2 lies somewhere in between. Like 2 is my head. It lies somewhere in between. When I keep pushing 1 and 3 closer, and eventually like I make it a single point. So 2 will also eventually lie on the same point. 2 will also be the same point, right?
Yeah, right.
Right? Okay. So if 2 is the same point, this was already equal to 0. It also implies that this will be equal to 0. Summation of lambda I. This will be equal to 0, right? This part will be equal to 0. right?
Mm,
This part will be equal to 0, right?
this
This is a
where
complementary
we
slackness, right?
get.
So I know that that's why I was saying that it is just an extra. You don't have to worry about it. I was just trying to give you the intuition, like how does the complementary slackness pops in. It is not that we simply write it as a equation. It is how it comes into the picture. Okay.
Okay, I got it. Like that should be 1 and 3 should be equal. So because of that,
And therefore 2
mhm.
should also be equal to 3,
Yeah,
right?
that's why the
2 and
middle
3,
terms should
2
go to
if 2
0.
and 3 are equal, this means that it has to be equal to 0 because this
Yeah,
term is
yeah.
already equal to 0. So
That is
therefore,
already equal to the second term
yeah,
will go to 0. Yeah.
right. So that's all from my side. So thank you for joining and thank you. Like if you have any question, you could definitely like ask on the discussion forum and we'll try to reply as soon as possible. Okay. Thank you for joining.
Oh, thank you.